There are four different types of intermolecular forces, or forces that are between different atoms or compounds. And the reason we do not call these bonds is because they're not a bond, they are a force. They're actually more similar to an ionic compound, if you will. And the first type is called a London dispersion intermolecular force. Then we have a dipole to dipole intermolecular force. Then we have an ion to dipole intermolecular force. And then we have an ion to ion intermolecular force. Okay? And these are listed from weakest to strongest. And the strength of the intermolecular force can give us can give us a prediction about about the state of matter there. So this relates to polarity. So let's go through and look at this. Okay. A London dispersion intermolecular force is really the presence of no intermolecular force. I mean, it's a very, very weak force that's just there because these things have electrons that are moving around, and sometimes you can get a little interaction, but it's really essentially no force. It's a low force, L for low. So this is happening between two nonpolar substances. Okay, so you can have something between two that are nonpolar, and they're going to be really stretched out. Okay, or you can have it between something that's nonpolar and polar. It's kind of like hexane with hexane. Okay, it's a really weak intermolecular force, or something like hexane and water. Okay, and when you have a London dispersion force, we really predict that the state of matter here is a gas. It's really, really spread out. An example of something like this would be if you had like hydrogen gas with itself. Okay, so totally nonpolar, and we draw these little dots to indicate the presence of that London dispersion force. Now, these dots have no orientation. They're not going towards the H's or the H's. If this was a polar molecule like H2O, we would still have just these London dispersion dots. Now, dipole-dipole is a different story. This is between a molecule that is polar and another molecule that is polar, and we're going to see those strong dipole interactions. And just as the name would have it, we have dipoles present. So a standard example would be water. Since water is a polar molecule, that's partial negative, that's partial positive. This dipole right here, hey Changa, and this dipole right here are going to form a dipole to dipole intermolecular force. Notice that the water molecules are not as spread out as the particles in a London dispersion intermolecular force. Now, if I put in something else in here who's also polar, let's say I put HCl in here, partial positive, partial negative, there's your dipole to dipole force as well. So a dipole to dipole force is when you have polar molecules that have dipoles. We could draw the arrow here. This is a dipole. Dipoles that do not cancel are interacting with the other end of the dipole, kind of like a head to tail effect, right? This is going to be the partial positive side. This is going to be the partial negative side. This is going to be the partial positive side. This is going to be the partial negative side. And there is that dipole to dipole interaction. So again, it all depends on the temperature of the environment. However, we would predict that these things are liquids here. Ion to dipole is a little interesting, and it's very easy. It's even stronger than a dipole-dipole interaction. And this is when you have somebody who is actually an ion from an ionic compound. And these are going to be attracted to something that is polar. Okay, or up here I've been using the term P for that. So let's just use that. So an example would be this. Let's say I had this chlorine ion. Okay, and I connected it with water. Well, the Cl that's minus is going to be attracted to the part on water that's partially positive. And there's the attraction. So it's an ion to dipole. Here's the dipole from a covalent compound, and here's the ion. So we call this an ion to dipole interaction. Now, if this came from salt, sodium chloride, we know that we have a plus and a minus here. That positive Na plus would then go right there and form another ion to dipole. Now, sometimes these things can coagulate into solids, but normally we think of these as liquids, and specifically, actually, we would think of it as a solution, an aqueous solution here. And then the last thing is an ion to ion, and I'm showing you this because really, this is an ionic compound. Okay, and this is the strongest because there are no partial charges. So you look here, partial to partial, connected much more than we would see with this London dispersion force, where they're just really spread out because they're all nonpolar. Then here you have ion to dipole. Okay, now here you have ion to ion, and remember, all along I said that ionic compounds aren't really bonded. It's more of an attraction. So we're going to go ahead and think of an ionic compound in the category of an intermolecular force. So if we have something that's an ion connected to another ion, like a positive and a negative, that's the same thing as saying like Na plus and Cl minus. And there is the ion to ion interaction, and this is why salts, things like sodium chloride, tend to be solids at room temperature. Okay. So I want to make sure you have all of these down in your notes, and then I'm going to have you go through and fill out this entire intermolecular force diagram. Okay, and you can never do this enough, and I want you to stop here at molarity. Don't go on any further. So I'm going to do 3 of them, and then I'm going to have you guys finish the rest. Okay, so the first one I'm going to do is water with itself. Well, water with itself has already been done right here. So it's going to look like this, and it's going to be a liquid. Let's go ahead and do CO2 with itself. So when you do CO2, oh, oops, I shouldn't draw these because this molecule is nonpolar. That cancels with that. So because it's nonpolar, we're going to draw them really far apart, and the force in between them, okay, is going to be called a London dispersion force. And the state of matter is going to be a gas. Again, these little markings there are really light. They're not really going between the carbon or the oxygen. They're just there. Let's do H2O with HF. When you do these out, you will see that they are polar, so I'm going to leave the partial charges there. And we see that this is polar. Okay? So the positive side of it is here, and that's going to line up here. So that is called a dipole to dipole interaction, and this would tend to be a liquid. We can go through here some more. Remember, if things are nonpolar, okay, and I'm going to go through here and tell you that this is ionic, that this is ionic. Both of these are ionic. This is an ion. It's just one ion. It's this OH minus ion. Any other ions? Okay, so let's do one of the ion ones so you know what to do. Let's go ahead and do this here. So we know that this is going to break into Na plus and Cl minus. So water is going to look like this. Okay, covalent. The Na pluses are going to go here, and the Cl minus is going to go here, to either one. And this is an ion to a dipole. And this here is an ion to a dipole. Okay? Because it's a dipole from a covalent compound with an ion, tends to be liquid, and it's actually a solution. There. We're just going to call it a liquid for now. So I want you to finish all of these off, please, and show those to me when you get back next time. Pay close attention to the fact that as long as something is nonpolar, even if it's with something that's polar, there's going to be no attraction. They're going to be really dispersed, and they're going to tend to be gas at room temperature. If you have two things that are polar, the partial positive part of the dipole will interact with that partial negative part of the dipole. They're going to interact, and those tend to be liquids at room temperature. And if there's an ion, that positive or negative ion is going to attract to that dipole, and we're going to call that an ion-dipole intermolecular force. And your typical ionic compound would be ion-ion. If I put another ionic compound in here, like NaF, the Na plus would go here, and the F minus would be here. And we have this huge lattice, really strong lattice, we call it, of ions.